Hello everyone, this is Professor Keen. This is a series of lectures that I've been giving about Newton's Principia. It's from chapter 23 in A Student's Guide to the Great Physics text, volume 2. The name of this chapter is Newton's Third Law and the Power of Machines. This chapter is largely devoted to understanding, as the previous chapter was, the implications of accepting Newton's three laws of motion. And so I think I want to spend a few minutes talking about some of these applications. I anticipate this chapter will probably take me maybe 3 or 4 lectures to go through. So again, this is from Newton's Third Law and the Power of Machines. And the reference is A Student's Guide, volume 2, chapter 23. So chapter 23. This is from Newton's Principia. He begins this chapter by talking about the relationship between his work and the work of Galileo before him. You might recall that we studied the work of Galileo Galilei in the beginning of this semester, and Galileo had been studying projectile motion. He found that when you drop an object, the distance that the object falls is proportional to the square of the time of fall. If we wanted to say this in terms of an equation, we'd say distance equals 1/2 gt squared. Or more particularly, we could say distance is 1/2, let me erase this and say distance is 1/2 at squared, where a is the acceleration that the object feels. Remember, this formula works whenever the acceleration is constant. So for a equals a constant. That is for the case of uniform acceleration. So that was the first thing that Galileo had talked about. And another thing that Galileo talked about is for projectiles, that specifically projectiles exhibit parabolic motion. He says semi-parabolic motion. Okay. Now what I'd like to do here is make a connection, and this is what Newton does at the beginning of this chapter. He makes a connection, excuse me, he makes a connection between the work of Galileo and Newton's laws of motion. So let's try to do a Newtonian analysis of parabolic motion. So when an object is fired, it's moving through the air, we can represent the forces acting on it by a free body diagram. Okay, so here would be a mass. We'll call this mass M. And let's indicate all of the forces that are acting on it using arrows. And if it's going through the air, there is first of all the object's weight. And if there is any drag acting on the object, that would also be represented by a force. So for example, if the object was flying to the right, then the drag force would be to the left. It would counteract any motion. But you might recall that Galileo neglected the effects of drag largely when he was studying parabolic motion. So we too are going to ignore drag for now. And if that's the case, then there is only one force acting on this object while it's in motion. So there we have it. We have drawn the free body diagram for this projectile. Okay, so that's step 1, is draw the free body diagram. Step 2, you might recall, is setting up a coordinate system and writing Newton's laws of motion in component form. So let's set up a coordinate system. I'm going to draw the coordinate system like this. We'll use a Cartesian coordinate system where we call the horizontal direction x and the vertical direction y. For convenience, let's make the y direction pointing downward, because we all know that this object is going to be falling downward. Okay? And then we'll write down Newton's laws of motion, specifically Newton's second law, which says that the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction, and the sum of all the forces in the y direction provides the acceleration in the y direction. So these are our x and our y component forms of Newton's second law. Okay? Now, let's see where we can go with this. What are the forces in the x direction? Well, in the absence of drag, there are no forces in the x direction. So that means we can write this as 0 equals mass times acceleration in the x direction or more specifically, since the mass is not 0, that means the acceleration in the x direction must be 0. Which kind of makes sense. Remember what's happening is that since the acceleration in the x direction is 0, the velocity in the x direction is a constant. That is, it is moving with uniform horizontal speed, which is precisely what Galileo had claimed when you have a projectile. That horizontal speed would be 0 if you're simply dropping the object, or it could be some non-zero value like 10 miles an hour or 500 miles an hour or whatever it is in the horizontal direction for parabolic motion. Okay, so whereas Galileo simply assumed a constant horizontal speed, what we're doing here is we're showing how that constant horizontal speed arises from Newton's second law. Okay, what about in the vertical direction? Well, the force in the vertical direction is just the weight pointing downward. That equals mass times acceleration in the y direction. Where do we go with this? Well, we know the relationship between weight and mass. It's just mg, so that's the conversion between weight and mass and force. Sorry, weight and force. So mg equals mass times acceleration in the y direction. And we can see an m over here and an m over here. We can cancel those out. And so we find the acceleration in the y direction is just equal to g. G is 9.8. So we're saying that the acceleration in the y direction, let me get rid of these two right here. The acceleration in the y direction is g, which tells us that the acceleration is constant. If the acceleration is constant, well, then we can just use all of the old Galilean formulas. So that also implies that if the acceleration in the y direction is just constant at g, that means the velocity in the y direction is going to be g times time, because that's the acceleration times the time. And we can also use the distance that it moves in the y direction is 1/2 gt squared. So all of the stuff that we inherited from Galileo that follows from the constancy of the acceleration can readily be used now, but once again, now the idea is that this follows from Newton's laws of motion. So whereas Galileo was simply interested in describing the motion of objects, Newton is interested in understanding the cause of their motion in terms of forces. So that's the insight that Newton is providing us with. Okay, so we can do all the stuff that Galileo taught us now. We can write down the velocity in the y direction as a function of time. It's linearly increasing with time. The slope of this is just the acceleration in the y direction, which we found is just g. And we can talk about the velocity in the x direction, for example. Velocity in the x direction. It's a constant. Whatever the initial horizontal speed was, the velocity remains constant in the x direction. And so we can do all the same kind of stuff. Okay, tell you what, I'm going to stop there after having talked about the connection between Newton's laws of motion and the work of Galileo. And the next thing I'm going to do is talk about collisions.